So now we're going to talk about concentrations of solutions and how we can express those quantitatively. Concentration is the amount of solute dissolved in a given solvent. In the previous video, we discussed solute, solvent, and electrolytes versus non-electrolytes. But now we're going to talk about concentrations and how we express that numerically. If we have a concentrated solution, there is a higher ratio of solute to solvent. So it's more concentrated. And in a dilute solution, so these are qualitative descriptions, not quantitative. We're going to talk about these in quantitative terms, numerically. So, just for comparison of a concentrated versus a dilute solution, concentrated solutions have more solute particles per unit volume than dilute solutions, which have fewer particles per unit volume. The most common quantitative expression of concentration in chemistry is molarity, and this is the ratio of moles of solute per liter of solution. So M equals moles solute divided by liters of solution in those units, moles per liter. Oh, I didn't have to write it. It's okay. Ways to abbreviate molarity, capital M or in brackets. You'll see both. And we can rearrange that molarity equation and use it as a conversion factor. And we'll do some examples of that. So molarity by definition is moles of solute per liters of solution, but we can rearrange that and find volume. If we have molarity and number of moles, or we can determine number of moles when we have molarity in liters by multiplying those two. So it can be used as a conversion factor. So here's an example of a problem. We're asked to calculate the molarity of a solution prepared by dissolving 45 grams of Ki into a total volume of 500 mils. So remember, molarity equals moles of solute. Our solute here is Ki divided by liters of Ki solution. So that is a combination of the solute and the solvent. So solution equals solute plus solvent. Okay. So in order to calculate the molarity of this solution, we first have to convert grams of Ki to moles of Ki and mils of solution to liters of solution. And then we can set up our molarity equation. So we have 45 grams of Ki. We need the molar mass to convert that to moles. And that molar mass is 166 grams of Ki per 1 mole. So we have 0.271 moles. And we want a total volume of 500 mils. But we need to convert that to liters. So for 1,000 mils in 1 liter. So we have 0.5000 liters of solution. And now we can calculate molarity. 0.271 moles divided by 0.5000 liters of solution. And our molarity then is 3 significant figures because we're limited by the moles. 0.542 molar Ki solution. So another example, how many mils of 3.50 molar sodium hydroxide can be prepared from 75 grams of sodium hydroxide? So now we're asked to find the volume in liters. Well, actually, we'll find it in liters and convert it to milliliters. So we'll need to use that molarity as a conversion factor. So we have 75 grams of NaOH, which we have to convert to moles. This tells me that I have 3.50 moles of NaOH in 1 liter of NaOH solution. So I need the molar mass here, and this is 40.00 grams of sodium hydroxide per 1 mole of NaOH. And now I can use that molarity to convert to the volume in liters. So we have 3.50 moles NaOH in 1 liter of NaOH solution. Got rid of our grams, moles. Now we have liters of solution. We're asked for mils, so we have to now convert those liters to mils. And when we do that math, let's see, we get 535 milliliters. So why 3 significant figures here? We have 4 here in our mass, but our molarity is based on measurements. So density and molarity are going to be conversion factors that we do have to pay attention to this. This is an exact number, but this is a measurement. We had to measure a certain mass of sodium hydroxide to get that 3.50 molar solution. So we have 3 sig figs in our final answer. Now, there's another way to prep solutions, and that's by dilution. And this is the process of diluting a more concentrated solution to prepare a less concentrated solution. The moles of solute before the dilution are going to equal the moles of solute after the dilution, but the volume will be different. Okay? So moles of solute is equal to moles of solute over liters of solution times liters of solution. In other words, I use a different subscript, but the dilution equation, and that's what this is, I use M initial, V initial for volume, M final, V final. This is the dilute, this is the concentrated. So for example, the class will need 250.0 mils of 0.10 molar copper 2 chloride solution. And in the stockroom, there's a bottle of 2 molar copper 2 chloride solution. Describe how to prepare the solution. How much of the 2 molar solution do we need? And so we'll use that M initial, V initial equals M final, V final. And what we're going to look for is V initial, because we need a volume of that initial concentration in order to come up with the other given. So M initial equals 2.0 molar. V initial is what we're looking for. M final is 0.10 molar. And V final is 250 mils. So we're just going to rearrange that. V initial equals M final, V final over M initial. I'm going to substitute my variables in there. We have 0.10 molar times 250 mils divided by 2.0 molar. Polarities cancel, and so we'll get a volume in liters, and this is the volume of that 2.0 molar copper 2 chloride solution that we need to dilute. So this is 12.5 mils. So when it comes to describing how to prepare the solution, we would say we would measure 12.5 mils of the 2.0 molar Cl or CuCl2 solution and dilute it to 250 mils in some glassware. The more precise that glassware is, obviously the better or more precise your molarity is going to be. So solution stoichiometry. We've talked about electrolytes. They dissociate 100% in solution. So soluble ionic compounds completely dissolve in solution. And by using mole ratios, we can calculate the concentration of all of those ions in solution. So we've already seen that sodium chloride dissociates into sodium ions and chloride ions. But if we have sodium sulfate, that's going to dissociate into 2 sodium ions and 1 sulfate ion. Or aluminum chloride dissociates into 1 aluminum ion and 3 chloride ions. And we can determine the concentration or the molarity of those ions from the molarity of the solution. So, example here, find the concentration of all species, and that means the ions, in a 0.25 molar solution of magnesium chloride. So if we write an equation that describes what magnesium chloride looks like when it's dissolved in water, we've got a magnesium ion and 2 chloride ions. Yeah, I shouldn't have had to write that. We're told the concentration of that magnesium chloride, or its molar concentration. So to determine the concentration of the ions in the solution, we need to use that molarity and the number of ion units. Well, we only have one magnesium ion per formula unit, so the concentration of magnesium is 0.25 molar. However, when it comes to chloride, we have 2 chloride ions. So we have to multiply 0.25 by 2, and our chloride ion concentration is 0.50 molar. And that would apply to all ions. So here's another example here. This is asking us to use the square bracket notation. So remember, you saw that you can indicate molarity by using brackets to express the molar concentration for all the ions in these solutions. So barium hydroxide, when it dissolves in water, will have barium, 1 barium, 2 plus, and 2 hydroxide ions. Okay, so the concentration, the molar concentration of barium 2 plus is going to be the same concentration as the solution itself. However, the hydroxide concentration is 2 times that. So 0.84 molar here. And here we have, when this dissociates, we get ammonium ion and 1 chloride ion. And this is a 1.2 molar solution. So each of those concentration or ion concentrations is 1.2 molar. So think about it this way. You have 1.2 molar, or that many number of moles per liter of this compound. And when it dissociates, you've got the same number of moles of each of those ions. Okay, so they're just going to be ratios of whatever that original molarity is. And I have one more problem that I'm going to do here. And this is kind of combining stoichiometry and molarity. And I have a balanced equation. Al2CO3. This is a solid. Then we have 6HCl aqueous. So that is an aqueous solution of HCl. Our products are 2Al, Cl3, solid. So we form a solid in this reaction. Whoops, I'm sorry, I didn't mean to put an arrow there. That needs to be plus 3 moles of CO2 gas and 3 H2O Cl. Okay, and the question here is, what volume of a 0.800 molar HCl solution is needed? To produce 30 grams of AlCl3. So to start with, we're given this, and the molarity of that HCl is a conversion factor. Remember, molarity we can write as 0.800 moles of HCl per 1 liter of solution. So in order to use this, we need to get a molar relationship between ACl3 and HCl, which we can get from the balanced equation. But first, we have to convert our grams of AlCl3 to moles of AlCl3 using molar mass. Then we can convert from moles of AlCl3 to moles of HCl. And then, using the molarity, we can convert to volume of HCl. So we're going to use that molarity as a conversion factor. And the stoichiometry from the balanced equation. So that's the stoichiometry. This is molar mass. And this is molarity. So, this will be our last example on this video. Again, the molar mass, 133 grams of AlCl3 in 1 mole. And from the balanced equation, we have 2 moles, sorry, this is AlCl3, 2 moles of AlCl3 to 6 moles of HCl. So now we've gone from grams of a reactant to moles of the reactant, or product, sorry, to moles of the reactant, the HCl. And now I can use that molarity to convert to the volume. And we want to get rid of the moles of HCl. So the 0.800 moles go on the bottom, and 1 liter of solution on top. And do the math. And let's see, it is 0.844 liters of HCl. Whoops, don't do that. That is 0.800 molar in concentration. All right, visit an office hour if you need help or have questions. Thanks.